squared is 1, guys.
Well, look at arguing like it's not 1.
Yeah.
It's 1.
Okay, I'm hoping that the first 10 go rather quickly, and then the next 10 might slow you down just a bit. You not only need to know these when we start working with radicals, you're going to have to memorize some of your bigger ones too. You're going to have to memorize, for example, 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed, 7 to the 2 to the 4th, 3 to the 4th, and so on. Not a lot of them, but there's some. Okay, these are called perfect squares. We're going to be looking for these. Of course, I assume that everybody has the first column here. This is 4 and 9 and, without looking, 16 and 25, 36. And the next one, 64 and 81 and 100. Now, 11 squared, most of you know it already. How many of you know the trick for multiplying by 11? 2-digit number times 11? You may have seen it before. Number sense? Did you do number sense?
I thought you just add the 11 to the front. Yeah.
No, okay. Here's what I'm talking about. Somebody give me a 2-digit number. 22 times 11 is 242. Now the way that you do this is I simply add the two numbers together to get my middle. Watch. Say it's 71 times 11. Add the two numbers. So it's 781. Now sometimes you have to do a carry along with that. So if there's a carry involved, it makes it a little bit harder, but isn't that bad? Let's say I have, I don't know, 39 times 11. Well, you end up with the 9 at the end and the 3, well, it's not 3 because you're going to have to add them together to get the middle number. What do you get when you add those together? 12. So you got to carry the 2 and then it makes that a 4. I just add the numbers to get the middle term. So, 517 times 11, we write down the 7. You add these two to get that. 8. You add these two to get this one. 6, and then there's a 5 at the beginning. This is a trick for multiplying by 11. Well, that makes 11 times 11 pretty easy. 121. Most people know 12 squared. 144. A lot of people slow down at 13 squared, but that's the easiest number of all. 1, and your favorite number? 69.
Oh, 69.
And then when you're done with that number, 1, 96. Yeah, that's right. What happens? One of the things I want you to keep in mind is that when you're learning something new, there's an easy way to remember anything. If you want to remember something, make it weird. Make it strange or unique. Come up with a good, weird way of making a connection and you won't forget it. You guys will probably remember 13 squared. And 14 squared, possibly. If you got the joke. If you didn't, that's okay. Here's the point. We remember things that are odd or out of place. And the weirder they are, the easier they are to remember. Did I give you guys this lesson before? Yes? With the car? Yeah? Yeah? There's a car coming toward you. Okay, everybody, I want you to imagine you're driving down the road. There's a car coming toward you, and it's a blue Oldsmobile driven by a businessman, and he goes past. How long do you think you'll remember that guy in that particular car? 2 seconds? 1 second until another car passes you, right? Now, imagine the same exact scenario. You're driving down the road, and coming the other way is the Oscar Mayer Wienermobile driven by a one-eyed clown. For the rest of your life, on your deathbed with Alzheimer's, you will not get that image out of your head. And the reason? It's absolutely unique. Whenever you have something that you need to remember, make a little scenario in your head and make it unique and strange. The stranger you make it, the stranger the connection, the better you remember it. Now I'm going to show you a way to remember your 15 squared. It's your second 25. Didn't you have a first 25? I have a second 25. Easy to remember? My third 25 is next. 16 squared also has a 25 in it. It's the first two digits. Since I know what the first two digits are, it's easy to find the last digit. Just square 6. Since it ends in 6, we know it ends in 6. Now there's a trick for the next ones. How many people wrote them down? How many people wrote down the next 3? Okay, if you haven't written down the next 3, if you have, take a look for the pattern. There's a pattern of the first two numbers. You multiply that number by 4, don't you? 7 times 4 is? 28. And 8 times 4 is? 32. And 9 times 4 is? 36. And those are the first two numbers. The last number we find by squaring this. This is 9. This is 4. This one ends in 1. And then you have 20 squared is 400. You don't have to know these, but it's nice if you have the pattern in front of you, and eventually you'll know if you'll memorize them. You want to know your perfect squares. Now, we need perfect squares because we're going to do a thing called reducing radicals. And it's a little bit like reducing fractions. You guys learned how to reduce fractions, so let's do that first. Let's take a fraction like 16 over 48, and you all learned to reduce this. You would divide by the same number on top and the bottom, and you would look for the common factor. What's a common factor for 16 and 48? 4, 8, 2. There's a lot of choices. 16 is the largest common factor. Now, it's fastest to reduce this by dividing by the largest common factor. It's GCF, greatest common factor. If I divide this by 16, it's faster. But with fractions, you guys learned that you could divide by any common factor that you wanted. In fact, I could even go by 2's, couldn't I? Divide by 2 and divide by 2, and it works. What do you get?
80.
Over 24. And now all of a sudden, maybe you see the 8. Divide by 8, divide by 8, and you get 1 over 3. All right. Now, we are going to reduce a radical. It's similar to reducing fractions. We are not going to look for a GCF. This is called greatest common factor. That's what we look for when we're reducing fractions. We're going to look for a perfect square factor. We want a factor that's one of these. Now the 1 is pretty worthless because 1 is a factor of everything. So that doesn't help any. If you're reduced by 1, nothing happens, right? Same thing with radicals. So we don't want the 1. We're looking for 4, 9, 16, 25, 36, 49. We want a perfect square factor. And I'm going to reduce the square root of 18. And I want to know which one of those numbers goes into 18. It has to be a factor. 4, 9, 16, 25, 36. 9, yes? 9 is a factor of 18? Now, at first, you guys are going to go through all the steps. You're going to factor this into 9 times 2. Then you're going to split this up. This is the square root of 9 times the square root of 2. And what is the square root of 9? 3 times the square root of 2. This is reduced. Now, later on, you guys are just going to eliminate those 2 steps. You're not even going to need them. Eventually, you'll go from here straight to there. But at first, you probably ought to use these steps. So let's take the square root of 8. Go ahead and go through the steps for me. This is one you're going to want to memorize anyway. What's the perfect square factor? It's got to be small.
2.
Okay, yeah, well, the perfect square factor is 4, yes?
Yes.
4 times 2. And then you separate it out. That's the square root of 4 times the square root of 2. I can't take the square root of 2. This is called an irrational number. It's really ugly. But the square root of 4 is just 2. Find the square root of 50. We're looking for a perfect square factor. Ashley and Greg? Oh, okay. Elena's not here? Kathy? Gonzalez? How about Chris? And Kristen Aguilar? Got it? What's your perfect square factor? We separate it into
2. 25.
25 times
2.
2. And now some of you are already starting to think about getting rid of this middle step. Be careful, because if you go too soon, if you don't practice first, I know it seems kind of obvious that you're going to be able to get rid of this step. Don't do it too soon. Let me show you what I mean. Everybody do square root of 32. How many people saw the 4? 4 times 8? Okay, I want to point something out, and this happens a lot. What happens is you're going to find a perfect square factor like 4, but then this one is going to also have a perfect square factor. Does everybody see that 8 can be factored some more? So whenever this happens to you, I want you to immediately do the following. I want you to change this by factoring out the other 4. Do you see what I did? Doesn't that make this part 16? What we want to do is we don't want the smaller one. We always want the largest perfect square factor, which in this case is 16. And that is the square root of 16 times the square root of 2, which is 4 root 2. Be very careful. A lot of people who start taking these out too soon will want to take the square root of 4. See what I mean? That'll happen a lot, so be careful. It's going to be tempting to do that. You don't, of course, because the square root of 16 is just 4, not the square root of 4. square root of 45 for me? What's the perfect square factor? What goes into 45? 9 times 5. Separated into two parts. This is the same as this. What is the square root of 9?
3.
3 root. You got it?
Yeah.
Let's find out.
Yeah.
Got a few of them this time of year. All right, what's your perfect square factor for this guy? What goes in here evenly? 10 times 9, yeah, 9 times 10. 9 goes into here. What about this one? 4. Got it? And this one? Same thing. 4 again. And this one? Big one.
4.
Bigger. Bigger than 25. 100 goes in here, doesn't it? And then this one? That's the 25. What we're looking for are perfect square factors. Let me remind you what those are. They are 4, 9, 16, 25, 36, 49, 64, 81, 100. As soon as you get to halfway, you're done. You don't have to go any further. With this one, yes, 4 does go into 200 evenly, doesn't it? Everybody see that's 4 times 50? But so does 25. 25 times 8. But so does 100. 100 times 2. We always want the largest perfect square factor. You don't want to start with the small one and then try and work your way up. You just want to pick the biggest perfect square factor. Which one of these goes into 90? 9 times 10. Separate them and take the radical. This one? 4 times 5. Or this one? 4 times 10. Do it yourself. You'll know when it's possible for you to start skipping those. I wouldn't recommend it right away. Just go ahead and write them out at first. What about this guy? Always write your perfect square first. 100 times 2. And the last one? Times 3. There you go. So we have square root of 9 times square root of 10, square root of 4 times square root of 5. I know eventually you guys are going to want to quit doing that and just write 2 root 10, aren't you? It's okay. You'll know when you're ready. Square root of 9. And this one, 2 root 5. This one's just 2 root 10. This one, 10 root 2 and 5 root 3. You need to reduce radicals because sometimes they're going to give you a problem where you have to add some radicals. Let me show you what I mean. Suppose I'm interested in, well, let me show you why we do this. When I was in high school, we didn't have, our calculators didn't do radicals. If you wanted the square root of a number, you had to reduce it and multiply it yourself. So if we wanted, for example, the square root of 50, we would have to reduce the radical to what? Everybody? All the way reduced. 5 root 2. And we had memorized the square root of 2. It's 1.414. And then we would multiply that by 5. And we get 7.07, and that was our estimate for the square root of 50. See how that works? Well, that's what we had to do. Now, you don't have to do that necessarily, but here's the problem. Sometimes your answer is going to be 2 radicals added together. Let's say the square root of 50 plus the square root of 200. This is an irrational number. That means that this doesn't end here. Do you understand that this keeps going forever and ever and ever and never ends? Never repeats? And the same thing here. But we can reduce this in a different way. What you can do is reduce this and then add them like they're variables. Try it. Square root of 50 is right there. Square root of 200, you know. So the square root of 50 is 5 root 2. And the square root of 200 is 10 root 2. And when you add these together, it acts a lot like 5 times x plus 10 times x, which gives you, take a guess, 15 root 2. This is the same if I add these two. So if I wanted to estimate this, I could take 15 times 1.414 times 15 and get my solution. Right? Instead of having to do this in 2 separate steps or something, I could get 15 times root 2. Now the reason why I showed you reducing radicals, part of it, is so that you could find out what to do when you have a radical in the denominator. It looks like this. And I want you to try this. Everybody take 7 root 2. And I want you to take 7 divided by root 2. I want you to compare those two things. Use 1.414, guys. 1.414 for the square root of 2.
1.414.
Mm-hmm. Okay, this isn't very difficult, is it? Just multiply seven times the 4, you get the 8, carry the 2, that's going to be 9. That's 8, carry the 2, that's going to be 9, and we're going to move the decimal 3 places. What y'all got?
Yes.
By the way, this is the square root of 98. This is exactly the square root of 98. Do you see that I would expect it to be a little bit less than 10? And why? The square root of 100 is 10, so the square root of 98 has to be pretty close to that. No? You got that so far? All right, now what I want you to do is I want you to take 7 and I want you to divide it by the square root of 2. This is approximately 1.414, and I'm going to divide 7 by this number. Remember what you do for decimal division? Yeah, you got to move it from here over 3 places. 1, 2, 3. So now, 1414, I'm going to have to guess. It looks like 5, but not quite. 5 would give me 7,070, so I only want to multiply 4 times, don't I? Go ahead. Do y'all see this is 5 times as much work as multiplying it?
5, 6, 5.
Yeah, 56, 56. We have to do the subtraction. It's 4. 4. 3. 1. 1344. There's a 0. By the way, there is a decimal right there. You need to bring down your 0. Maybe 9? Looks like 9 to me. Try it. I have a purpose in having you do this, guys. You'll see what it is in a second. There's something I want you to remember. 9 times 4. Let's see, I'm going to multiply this by 9. I'm going to get 6, carry the 3. That's 2, carry the 1. That's 7, carry the 3. That's 12. What y'all got? 12, 7, 26? And then we have to subtract it, so 6 from 0 is 4. That's a 1. 7. 5 this time. Did I get that right? Didn't make a mistake there, okay. So 5's next. Go ahead. I'm sorry?
Isn't it 6, 120?
Oh, no, I don't think so. No, it won't quite make it. Almost, but not quite. Almost makes it, but not quite. It's 5. Because it's 70, 70, isn't it?
Isn't the answer 6, 14?
Oh, I'm sorry. It's a 6 here? Did I forget to borrow? No, no, that's right. This is correct. 5 times 14, 14 is 70, 70.
Yeah. Okay.
And we have a 7, 0 left. .95 looks like a pretty close estimate. Does everybody see this a lot of work?
Yeah.
Compared to this? Now I want you to imagine, if you didn't need it to 3 places, what if you wanted to make it more accurate? Now imagine that you do this. Imagine, instead of 1.414, you actually know the next 3 digits, 213. Now if you want this better estimate, this is not that much more work. You just multiply by 7, right? But look how much more work you have if you want to divide it. Does everybody see that this gets pretty hectic? Now imagine if you were an engineer going to the moon in 1969, you do not have calculators that do this for you. And you have to be extremely accurate. Well, luckily mathematicians are lazy and they don't like doing this. So we do a thing called rationalizing the denominator. Do you all see that I'm taking 7 and I'm dividing it by an infinite decimal? Do you understand how impossible that is? How many places do I have to move this decimal? Forever, right? And I never get there? Y'all see the problem here? So here's what I'm going to do. I'm not going to use 7 over root 2. I'm going to use a trick. I'm going to simplify this by multiplying by what's called the conjugate. Take a look what you get. This is just 7 times root 2. And the square root of 2 times the square root of 2. What is that? Square root of 4. Isn't that 2? Oh, nice. You see, I don't have to divide by this ugly, horrible decimal. I can move it to the numerator by multiplying this thing and eliminating the radical. This is called rationalizing the denominator. This is an irrational number. This is a rational number. It's much, much nicer in all sorts of ways. Even for computers, it's easier for them to calculate this than it is to calculate this. And you do get the right answer. So let's do a little practice. We'll just do a few of them. I'm going to have you do 15 divided by root 3. Let's do 2 root 2 over root 6. Everybody multiply by root 3? You'll see I'm multiplying by the same thing on the top and the bottom, so I'm not changing the fraction. I'm just changing the form of the fraction. This gives me 15 root 3, and the square root of 3 times the square root of 3 is just 3. And what is this? Divide it.
Oh, it's
5 root 3, that's all. This is the same as this. Same thing. Try number 2. Number 2 is kind of hard. It's got lots of stuff in it. You're not only going to have to rationalize, you're going to have to fix it. Don't worry if you didn't get this one right, it's not that big of a deal, but it's the square root of 6. Did y'all get that far? Okay, this is going to be 2 times the square root of 12, isn't it? Got that? And this is over square root of 36, which is just 6. Square root of 6 times square root of 6 is 6. Now you can simplify this by dividing the 2 into the 6. What goes down here? 3, yeah. Now you're almost done. This would almost be correct, except that that can be reduced. 4? Yeah, it's going to be 4 times 3 is 12. And then you have to reduce it. I'll do it in steps. By the way, you can't simplify those 3's. That's the square root of 4 times the square root of 3 over 3. This doesn't look a whole lot like that, but there it is. Number 3 is going to be a lot easier. Go ahead and work those out. The other ones are easier than that one. I kind of threw that one in thinking we'd try a hard one, but 3 and 4 are going to be easy for you. Multiply by
2.
root 2. And I get 12 root 2 on the top. What's the square root of 2 times the square root of 2? 2. We can reduce this.
6.
Got that? One last one. 18 over root 3. We call square root of 3 the conjugate because it simplifies this thing. This gives me 18 root 3 over 3. And when I simplify it, you get 6 root 3. All right, the point to all of this is that you need every bit of this